Okay, well, thanks very much for having me. So I'm interested in the symplectic topology of ample hypersurfaces, what the algebraic geometers would call it. Of course, those things you can just say, well, a classic example, I don't know, an elliptic curve in CP2, a quintic threefold in CP4. In the end, it's just a symplectic manifold with a vanishing first Chern class. And it's just an example of such a manifold, just an easy example. But I've always thought that the fact that these things do appear as hypersurfaces, as divisors, especially I'm going to look at divisors that can be moved in a pencil, that should somehow have profound implications for the symplectic topology, which is what I'm trying to figure out. It turns out that this whole construction is so complicated that I cannot actually keep the entirety of it in my mind at one time. Okay, this is what it looks like. Okay, but thanks to the friendly people at the institute, I start at the top and I start checking off boxes, and I hope to sort of eventually get through to it. Okay, so of course you don't understand anything here, but I just did it so that later I don't. It's sort of a Stone Age version of having slides, so that I don't have to copy it out. Okay, so what is the situation that I'm interested in? Okay, so we start. Let's say I'm going to use algebra geometric language, even though it's actually everything works within purely symplectic geometry. So you could just replace the symplectic language. So start with a smooth Fano variety. So Fano is what the symplectic geometers called monotone. Fano variety of its complex of dimension n. With a Lefschetz pencil of anticanonical hypersurfaces. Okay, so the notation here is P is the Fano. So this is of dimension n, and M, complex dimension n minus 1, is the anticanonical hypersurface, is some member of this pencil, some smooth member, hypersurface. Okay, and this has vanishing first Chern class, so this is what I'm actually interested in. And there's a complex codimension 2 subvariety, which is the base locus of the pencil. Okay, so the picture looks like this. Okay, so this would be P, and in P there is this pencil of hypersurfaces, one of which is maybe M, some are singular, and they all go through the same locus, B. Okay, so example. So P could be CP2, and then M could be a cubic curve, or in other words, a 2 torus, and the base locus would be the intersection of 2 cubic curves, which is, say, 9 points. Okay. All right, so there's a couple of auxiliary geometric objects that I should do. Okay, so we can blow up B. So that separates all the different hypersurfaces to obtain a Lefschetz fibration. So you blow this up. Now it looks like this. So instead of your original, so this is the blow up. Say, okay, so notation. Okay, so this contains, this is now something that where you can separate all of them out. So, and it contains not just one copy of B, but now a copy of B in each fiber. And otherwise, the fibers are your same hypersurfaces as before. Okay? So this Lefschetz fibration looks like this. So there's this E bar. This is the blow up. Goes over CP1. And the fiber of that is your original M. Okay? And inside it is this locus here, CP1 cross B. I could just remove one fiber. Say, assume the fiber at infinity is smooth. I remove one pi. And if you remove one, then that's the same thing as removing a fiber. Okay, so this is, yeah, so, okay, right, and inside this we have C cross B. Okay. Okay, so in our running example, so E bar. So if P is CP2, then like this, then E bar would be CP2 blown up at 2 points. So it's sort of what's called a rational elliptic surface. Okay, and so pi bar has 12 nodal fibers. So which correspond to the singular members of the original pencil. Okay, so what I'm actually interested in, so consider the Fukaya category of M of the Calabi-Yau hypersurface. So in 3 versions. Okay. So there's the simplest thing is you could consider the Fukaya category of M where you remove the base locus. Okay. So now this is an affine variety, and so this is defined over, let's say, the complex numbers. Okay. So then there is the relative Fukaya category, where you, so this considers everything is disjoint from B. Okay, so there is, I will just write it like this, even though it actually uses B. So this has greater equal to 0 means it has greater equal 0 exponents. It's defined like this. So here the objects are Lagrangian submanifolds that are disjoint from B, but the holomorphic curves are allowed to go through B, and Q counts the intersection number with B. Okay, and finally, presumably there's the actual Fukaya category, F of M. Okay, so this is defined over here the Lagrangian submanifolds can intersect B, and so the relation is that if you set Q equals 0, you get this one here. So this is a deformation of this one here with deformation parameter Q, and this one here is after inverting Q. So this is, but this is not an equivalence, you just get it contained. So invert Q. Okay. But so from my point of view, this is maybe the central object, but this is the most familiar one maybe. Okay. So my question here is very simple, which is, so this is everything is defined over here, so all the things that you see, the multiplication maps in this category are formal functions of Q. The question is, what functions? Okay? What kind of? You realize immediately that in this generality, this does not actually make a lot of sense. Okay? You can think of it in algebraic geometry. You know, you could have a variety that's defined over something nice, let's say a polynomial, so the ring of Laurent polynomials. But you know, once you allow, that doesn't mean so. You know, so okay. Suppose you have a variety that's given over this, but it actually has a model over some smaller field. But that doesn't mean that all points of that variety are defined over the smaller field, right? You can have an elliptic curve given over the complex numbers that has a model that's defined over Q, but that doesn't mean that every complex point is a Q point. Okay, so because we're including all objects here, so you have to just ask the question slightly better. Okay, and the way to ask the question is so the Lefschetz vibration provides you with a notion of a particular kind of Lagrangian submanifolds with vanishing cycles. So it provides a non-unique but a basis of vanishing cycles. Okay, so say V1 up to Vm. Okay, and so these form full subcategories. So here we have, I will call this one here B naught inside this, okay, which have the same property. So just use these finitely many objects, and B inside B greater equal 0 inside F greater equal 0 of M, and B inside F of M. Okay, and the relation is the same. Here you set Q equals 0. In this case here, because the objects stay the same, you actually invert Q. Okay, so instead of talking about this whole thing, we'll just talk about these subcategories that have, finitely many objects. And I can ask, so this is here's a finitely many objects, but I can ask what functions of Q occur in it. But, remember, in principle speaking, these are A infinity categories, right? So they have infinitely many structure maps. However, there are A infinity categories which are, at least say for this one here, they are proper and smooth. There is abstract theorems in algebra by Toen that says that in principle it should be defined over a subfield of this one here that's finitely generated over C. But that theorem is purely abstract. It doesn't tell you how many generators or what that subfield could possibly be. Okay. Also, so the last moment of caution. Okay, so I have to. Okay. Okay, let me state the problem here. Okay. Okay, so we're looking for models of, this B is defined up to quasi-isomorphism. So model means you replace it by something that's quasi-isomorphic, that are defined over, geometrically relevant subfields of CQ. And the same thing for B greater equals 0 with subrings. Okay? So so there's obviously a practical advantage to this, right? Meaning in principle, whenever you compute something in B, you have this Q series, and so it's not a finite computation. But if you know in which field this lies in, you might get away with only computing the first so and so many coefficients in Q, and then the rest would be determined. Okay? And I should say a remark. I'll do it in this case here. So so you can recover the whole thing by some formal completion. And then the statement, so hence, if B is defined over some subfield K of this one here, the subcategory, it's not true that, because, again, there's this issue with points and so on, but the subcategory of f of m consisting of rigid objects, so objects that do not admit any infinitesimal deformations is defined over the algebraic closure K bar inside. So this is inside C, Q times 1 over N. Okay, this is the algebraic closure of the field of power series, field of Lorentz series in one variable. Okay. So if, in other words, if you have this, you can ask, well, I picked these particular objects here, but if there is a field, if the resulting thing has a model over K, then at least the subcategory of things that are rigid, that do not come in families, is defined for general reasons over the algebraic closure. Okay, which concretely means that if you have any Lagrangian submanifold that appears as an object of f of m, and say it's a homology sphere, then that will have its infinity structure will be defined over K bar, which gives rise to some interesting Galois theoretic problems. Like, are there different objects defined over various, so every object has a Galois group associated to it. But I'm not going to enter into this. So this is why you might be, so you might be interested in this. Okay. So now, I want to say, okay. So let me give you what I expect the answer to be in the simplest possible case, okay, which is this here. So assume, for simplicity, that the second Betti number of your original variety on which the pencil lived was just 1. Okay, so this is sort of called sort of a one-parameter model. Okay. Okay. So take the following. Genus 0, Gromov-Witten invariance. Invariance of the blow-up. Okay, so what do we do here? So there's an invariant that lies, well, it's a class in here, okay, as usual with the usual Q series, and it actually counts, so this counts holomorphic sections. Okay, which means it counts rational curves. Now I already erased it. E bar is fibered over CP1 with some singular fibers. It counts holomorphic curves which have degree 1 CP1, which are the same thing as curves that integrate the first Chern class to 1, and that's why you land in H upper 2. I'm not going to write down the exact definition here. Point out one. Okay, so you can take, the reason why there's a Q is because you take different homology classes and you sum them up with suitable powers of Q. So in fact, there's actually only one negative power of Q, which is this one here. Okay, so remember, I'm sorry, I erased everything useful, but remember inside this E bar, inside this blow up, there is this trivial divisor CP1 across the base locus, which is the exceptional thing from the blow up. And there are sections which are sort of CP1 cross a point. Okay? And those generally, fill up the CP1 cross B entirely, and so you get this class here. And they have a negative power of Q because you're counting the intersection number with this divisor here with Q. And everything else has a non-negative power. Okay? And there's also, you can count the thing that counts holomorphic bisections. Okay, so which things that are fiber 2 to, that map 2 to 1 to the CP1, and let me call this Z upper 2. I know the notation is kind of non-standard, okay? So these are because they have Chern class 1 higher, So you can ask how many go through a generic point. So that gives you a class in H upper naught, which is just so this one here I'm just going to treat as a single power series, right? This one here I want to extract the coefficients so that we have okay. So so by star, well, okay, we can write so Z1 as linear combination of so this class here, CP1 cross B, and the fiber class. So there are two cohomology classes in H2. Well, if your original P was not four-dimensional, it follows from weak Lefschetz that when you blow up, you started with something with second Betti number 1. When you blow up, you get something with second Betti number 2. And those are the two generators, so it's trivial. There's only one low-dimensional case, which is the case of CP2. Okay? And in that case, you can figure it out by hand for symmetry reasons, that even though the cohomology of the blow-up is much larger, that you can write this as a combination like this. So what I want to do is actually, let's invert this. Instead of writing Z1 as a combination of this and that, I want to write this one here as a combination of this and this, which is possible because of that formula here. Okay, so I write okay, so I write this one here as a linear combination of this here and the fiber class. Okay, so psi. So this is one function, okay? And this is another function, okay? So, okay, you're totally confused. Let's treat this as a black box, okay? So what I did is I used some very simple Gromov-Witten theory of this blow-up to extract 3 power series in Q, okay? One is this one here, okay? That's a power series in Q. The second one is this one here, and the third one is that one here. Okay? So I think we're good. Okay, so. Okay, so the expectation is that so there is a model for that one there, defined over so it's actually defined inside for a ring here, okay, CF inside C double bracket Q. So it's actually okay, this one here, so C double bracket Q, and in fact it's sort of f of 0 is 0, f prime of 0 is non-zero. Okay, so there's a single power series, and that is everything that occurs are actually polynomials in that power series. Okay, or in other words, since the power series satisfies this one here, you can also think about it like this. If I do a change of variables from Q to f of Q, then the dependence is actually polynomial in the new variable. Okay, so this is nice, right? It's really something that you would not expect the Fukaya category, even if you have a Calabi-Yau manifold and its second Betti number is 1. So its Fukaya category has one formal parameter. You would not expect that formal parameter to be able to be transformable into an actual polynomial, okay? Because, you know, in algebraic geometry, what happens is that, well, you know, this is sort of motivated by mirror symmetry. You have this formal parameter. This formal parameter is the formal parameter at some point of some one-dimensional moduli space. And the assertion here is that that moduli space is actually a rational curve. Okay? And then generally speaking, there's absolutely no reason to expect that. So, okay, but I will actually, you know, so this is sort of pointless. Okay, I should tell you what this f is. Okay? Where f is a solution, and it doesn't matter which solution because everything will be equivalent, solution of. Okay, now comes the scary part. Okay, let's look at this equation here. Okay, so let's see, there's some parts, it looks horrible. Some parts, however, we can understand. Okay, so the primes here are just Q derivatives. Okay, so all these things here are, you know, they're all constructed from our three functions, right? I said we have three power series in Q that are extracted from enumerative geometry, psi, eta, and z2. And those appear here in some horrible color. What is F? Where S is the Schwarzian differential operator. SF equal F double prime over F prime prime minus a half F double prime over F prime squared. This is a famous operator because of its properties under conformal transformations of the variable Q. Since we're sort of aiming for something that's some statement about rational curves, it's I mean about, you know, rational dependence. It's not it's kind of natural that it appears. So so this is a highly nonlinear third order differential equation. But remember, this is all formal power series, right? So I just solve it order by order inductively. So there's not quite a unique solution, but, you know, two solutions vary by sort of rational dependence, and that wouldn't actually change this field here. Okay, so this equation here determines this subring here uniquely. Okay, so let me give you an example. Okay, a running example. Which was P equals CP2, okay? And so if I blow this up, E is the rational elliptic surface. And M is actually T2, okay? So obviously, one of the first observations in the field of mirror symmetry is that, you know, when you look at the Fukaya category of T2, you see certain, you know, sort of modularity properties of the Q coefficients, and those should be explained by mirror symmetry. On the other hand, there's a separate observation which says that the enumerative geometry of the rational elliptic surface produces modular forms. So these all come very well together here. So the equation, so the Schwarzian equation. So you suffer a little bit with the Gromov-Witten theory of the rational elliptic surface. So the Schwarzian equation is then actually turns out to be quite simple. So it's SF. So all this side here simplifies, and it gives you E4 Q cubed minus 1 divided by 2Q squared equals 0. This is the Eisenstein series, in a Q expansion of the Eisenstein series, okay? and f of q is equals q minus 5q to the 4. So this when you solve this order by order, okay, so this agrees with the parameterization given by mirror symmetry. I would call this the inverse mirror map. Okay, which is not really surprising because, as I said, well, we're talking about the Fukaya category of the two torus, right? Still, this statement is actually stronger than what you usually see, and also, even though it agrees in this case here with the mirror map, there's no actual mirror symmetry here. I mean, usually when you look at this Q dependence in terms of mirror symmetry, what you use is you use some sort of Gauss-Mannian connection to differentiate in Q direction, and then you try to sort of characterize the given variable Q somehow intrinsically in terms of Hodge theory. There's no Hodge theory whatsoever here. So this is something that's special to Lefschetz pencils, and also the equation obviously. If you look through in the mirror symmetry literature, you see that sometimes things happen to the equations for mirror maps that happen to be given as Schwarzian differential equations, but the Schwarzian operator sort of appears and disappears without ever finding some sort of satisfactory explanation. But here, the equations always have this form. Okay, so what I would like to do, okay, which seems reasonable. Okay, so first of all, the way that I've stated this conjecture is actually, sort of a very weak version of what's actually happening. So I want to explain what is actually happening. Okay, and then obviously I have to give some attempt, at least start explaining what is going on here, right?
So are the coefficients of f have any enumerative meaning?
Not that we know of in this generality. Okay, so there's two things I can say. There's in the framework of the Gross-Seibert program, there's presumably some interpretation of the mirror map in terms of enumerative geometry. Also, you will notice that the coefficients are integers, which wasn't really obvious. In the framework of ordinary mirror symmetry with Gauss-Mannian connections, there is a proof that in general these coefficients are integers. That would say, haha, I just look at the proof and I'll just figure out what those integers means. But actually the proof uses p-adic Hodge theory. So good luck. Okay, so let me first explain to you what a better statement is of this type here. Okay.
What paper is it that proves that they're integers?
There is Vologodsky is one of the authors, and there's a couple of other authors. I'm sorry, I don't quite remember. Okay, but there's a proof for one parameter mirror maps that the coefficients are integers, which includes integrality of the coefficients of the J function. Okay, so but here I'm not actually using this Hodge theory, so maybe there's a simpler proof why they're integers in this context here. Okay, but I asked some number theorists that they didn't seem perplexed by my questions. Okay, so what I would like to say is the following thing. So let's look at this for instance, at this B0 more explicitly, okay? So this is a category with finitely many objects, but I can just think of it as an algebra, okay? So as this algebra, it's the sum of all the finitely many Hom spaces, okay? So, and these are just the Floer cochain spaces between those vanishing cycles, okay? So we can arrange so there's a particular Floer homology of VI. The VI's are vanishing cycles, so they're spheres. So I can arrange that the Floer homology of this one here on the chain level, that this is actually, there's the identity, or the sort of minimum of a Morse function. Okay? And this is the maximum. Okay, so then consider this part here, which is sort of half of it. Okay, so this is just, instead of the whole endomorphism, I just take this generator here, and then I take all those things that go forward. Okay. Okay. So this is automatically, this is an A infinity subalgebra. Okay. In fact, so as vector space, let's split. Let me actually split. So why is it an A infinity subalgebra? Well, for really simple reasons, right? I mean, if you have a bunch of sort of, forward pointing, so they increase the index morphisms and you compose them, it's forward pointing. If you compose a bunch of EIs with themselves, it can only be EIs for degree reasons. And similarly, if you compose this and this, you will land in there. So it's nothing somehow smart here. So let's split B0 as A0 plus some complement as a vector space. And give. So now I'm going to introduce another grading, so to speak, here, which I will call the weight grading. It's got nothing to do with weights in Hodge theory. Sorry, that's just, I ran out of words in the English language. Okay, the weight grading, where I say that the weight of A0 is 0, and the weight of P0 is -1. Okay. So then the A infinity structure of B0, so this is an A infinity algebra, has pieces of weights 0, 1, 2, 3, and so on. Okay? So what does it mean is you can't have a multiplication, a composition, which actually decreases the weight. That's pretty much almost the same as the statement that A is an A infinity subalgebra. Okay, but this again, this comes from the ordering conditions and is not particularly exciting, maybe. Okay, but so the same thing. Okay, now I have a. Okay, I have several bad choices. Okay, let's go over here. Okay, so the same holds. Okay, so the same holds for the other versions, that B greater equals 0 and B and so on. So they all have this kind of weight structure filtration, and then the conjecture is that. So the form of that conjecture here. So for each W greater equal to 0, the weight W part of the A infinity structure of this one here is a polynomial of degree less or equal W in this function f. Okay? So for instance, you start with the weight 0 part, which is the sort of compositions of forward pointing things. And, oh, I'm sorry, yeah, so composition of forward pointing things. They are a polynomial of degree 0 in this, which means they don't depend on Q at all. It's just constant, it never changes, okay? And then there's the weight 1 part that is linear, okay? So this is the first conjecture, okay, that's the second part, and third part. The weight greater equal to 1 part determines up to quasi-isomorphism. Okay, so basically all you need to know is you need to know the weight 0 part and the weight 1 part. The weight 0 part is constant in Q. So you can just set Q equals 0, and it's just a question, what do you do in the affine variety, M minus the base locus. So that's a finite computation. It's a finite amount of information. It's given by finitely many rational numbers, okay? And then the weight 1 part is linear plus constant in F, okay? So all you need to know is the coefficients of the linear plus constant, which again, it's not obvious from here, but there are finitely many, okay? And then you need to know, so basically what it means is you can reconstruct this Fukaya category of this Calabi-Yau hypersurface from a finite amount of rational numbers that are actually fairly easily computable in practice, accessible, and this single function f that you extract from Grobov-Witten theory. Okay? And really, if you needed to know any part of this infinity structure here, you figure out, okay, you have this composition here that you want, what is the weight, okay? And then you run your computer, which solves this thing here and iteratively computes it up, starting from weight 1. Okay, so this is the explanation for what's actually going on. So in a sense, okay, so what is this motivated by, right? So if you think about, the deformation theory of, say, algebraic varieties, it's quite complicated, right? But if you think, so if you have, how do I characterize the deformation of a given variety, usually there's some deformation space, but it's sort of nonlinear space. But if you think of deformations of a divisor in a fixed ambient variety, all that you need to know is the ambient variety, which is constant, that corresponds to the weight 0 part, and what is the equation defining the divisor, which is sort of a linear problem. And then you can derive the entire variety from this, okay? And this is, so okay. As I already said, one of the pleasant consequences is that since it's a polynomial ring, once you make this change of variables from Q to f of Q, the Fukaya category is no longer a perturbative thing, which is defined, as a form of power series, but it's actually polynomial. You can specialize it to this parameter f of Q equals 1 or minus 3, and each of them is a nice category of a C, okay? So we sort of get away from the perturbative locus. Of course, this non-perturbative expansion, you could not expect it to be a symplectic invariant of the Calabi-Yau hypersurface. It depended on the hypersurface being embedded in P. Okay? But still, it's interesting. I call this the non-commutative pencil associated to the given pencil, this family of categories. You could call it the mirror pencil, but somehow, I'm not sure if mirror symmetry is the right word for what's happening here. Okay.
Can you explain that? How you assume a reference to a compact Lagrangian? I mean, you say model, but I'm a little worried about if you just have a compact Lagrangian. What is it about the endomorphism after that?
So if you have a compact Lagrangian, the first thing you need to do is you need to write it in terms of your vanishing cycles. So some kind of resolution in terms of vanishing cycles.
But by model, do you mean the coefficients are automatically going to be in some smaller ring, or they could be arbitrary?
Well, if you compute it sort of analytically, right, the coefficients could be anything. They don't mean anything because they're not uniquely determined. They're determined up to quasi-isomorphism. But if the Lagrangian is rigid, you can always find some quasi-isomorphic structure that's defined over the algebraic closure of C bracket F. Okay? That is, so the construction for just the vanishing cycles is very algorithmic. Obviously, if you wanted to say, well, how do I make a consequence about this particular Lagrangian submanifold that I'm interested in, that is not strictly algorithmic. Sort of your job to express that in terms of the vanishing cycles And you might find it easy or find it very hard. Okay.
What about for this particular example? I mean,
Which one?
Just the torus, the elliptic.
Well, I mean, for instance, in CP2, there's the elliptic curve. You have various curves, and you know very well how to express. I mean, those are not rigid, but certain ones you can express, and yeah, you can sort of get the usual consequences by resolution. So this example, that's sort of not really. I mean, you aren't going to get anything fundamental in this particular example because we understand it completely. The interest of this kind of theory is that you get statements which hold, fairly generally. Okay, so now, what is going on here? Okay, so somehow we have to get to this category here from all the way up there. Okay, so the last part here actually is which I will not describe, which is it's what's responsible for this part 2 of the statement, some kind of obstruction theoretic statement. Okay, and the corresponding obstruction theory, why this works out without any issues, uses an idea that well, you can probably approach it in various ways, but uses an idea that I learned about from Sheel Ganatra. It's not supposed to be mysterious, but there's some work to be done. Okay, so that's the bottom. But I think the most interesting case to start is at the top, where you start to say, okay, I am not going to take this one here lying down. Okay, you have to tell me what's going on with this. Okay, and I will tell you. Okay, so the first occurrence of the Schwarzian operator historically, sometime in the 19th century, is exactly how it occurs here, which is which is in terms of second-order linear differential equations. Okay, and for this particular monster coefficients here, so consider the ODE. Okay, for the following ODE here, for a function of Q, again, this is a formal differential equation, but now it's a much simpler differential equation, rho double prime. It has our usual coefficients, and you'll see them coming up. Okay, but it's much shorter to write down. Minus 4 z2 psi rho equals to 0. Okay. So then the quotient of two linearly independent solutions. So f is equals to rho 1 divided by rho 2 satisfies, okay, let's do this one here, satisfies that one here. Okay, so this is a well-known statement that the quotient of two linearly independent solutions of a linear order second ODE satisfies an inhomogeneous Schwarzian differential equations. Okay. So in other words, why do I care about quotients of solutions? Well, one way would be to say this. Okay, so solutions of this equation here have the form okay, so you start with one solution. Okay, so rho 1 times alpha plus beta f of q, where alpha and beta are just complex numbers. Okay, I mean, that's exactly the same thing that I said. The quotient of two linearly independent solutions is f. So rho 1 is a solution, then rho 1 times f is a solution, maybe rho 2 times f is a solution. Okay, and otherwise there are these, you can just add weights. Or let me say it in even more informal terms. So after change of variables, Q replaced by f of Q and Q-dependent rescaling. So if you consider the equation, you're allowed to pass from a function rho to a function f of Q times rho. So this equation becomes just the usual equation d by dq squared equals 0. Okay. Which is the solution that has, so basically, you change to f of q, you rescale, you get rid of this one here, and then the solutions are alpha plus beta times your new parameter, which makes the equation second derivative equals to 0. Okay. So what I would like to say, maybe a good way to say this, would be to say this f is a change of variable which projectively trivializes your equation. So it brings it projectively into the standard form here. Okay. And that's exactly what we're somehow trying to do. We're trying to get something that's constant plus linear in our weight 1 part here. Okay? So this is the first step here. That's elementary. So the Schwarzian differential equation arises from a second order linear differential equation. Okay? That was probably no help whatsoever, because the question is, where does the second order linear differential equation comes from? Okay? And this is going to be the last thing that I can explain, okay, which is the second step here. Okay. By the way, maybe so this is the second step here. By the way, I should make maybe a point, since I'm not going to be able to obviously get through this whole thing, about the structure of this argument here. If I've drawn it, this strategy is actually built like a tent, okay? And the middle of the tent is this one here. There is some Hamiltonian flow cohomology group, a cousin of this one here, that's associated to a Lefschetz vibration, okay? And on this flow cohomology group, there will live this second order ODE. Okay? So then you simplify it down to something you can explicitly solve. It reduces to that sort of all elementary. You basically try to solve this equation here. And so this takes place, there will be something that it's an ODE, but taking place not in scalars, but in this vector space here. And then from that one here, that is Hamiltonian flow cohomology, that turns out to govern all these categorical structures. So you go down here by a sequence of maps that just basically go away from something geometric and give you this horrible categorical stuff. Okay. So what is going on here? So I should maybe so the symplectic cohomology of E. Okay. So E, remember. So remember we had E pi over C. That's a Lefschetz vibration. Vibration with phi by. So E is a non-compact symplectic manifold, but it's very mildly non-compact because this is a proper map. So essentially it has this, this non-compact direction in C. So this symplectic cohomology is a Z-graded, a CQ vector space. Okay. So symplectic cohomology is kind of, it's an invariant of non-compact symplectic manifolds, and it's, well liked because of its rich structure of algebraic operations. Algebraic operations, which obviously are all linear over this coefficient field. Okay? But I'm not actually interested in algebraic operations. I'm interested in operations that actually differentiate the Q variable. Okay? So suppose that, let's look at the cohomology class of the symplectic form in here, which which if you follow how it's been constructed is actually also the class of this divisor, Poincaré duo of this one D, is 0. If it were 0, SH star of E would be defined over C. Right? So this is what someone called the exact case. This obviously never happens because, if you restrict the class to a fiber, it's the cohomology class of the symplectic form of the fiber. But you'll notice that there's a certain, unpleasant discrepancy here, right? So this one here is a symplectic invariant, okay? But its structure, the statement I made, is governed by an equality that actually holds in ordinary cohomology, okay? But obviously, however we think about this, it should be governed by its own intrinsic properties, okay? So more generally, so there is a map. So it's actually a map from the cohomology of E with coefficients in CQ to the symplectic cohomology. Okay? And if omega E lies in the kernel of this map, so it's a weaker condition. I don't say this is 0, but only that it lies in the kernel of this map. Then, well, the symplectic cohomology actually tries to be Q independent. Maybe not fully successfully, but so in that case here, the symplectic cohomology carries a differentiation operator. Okay? So it's basically trying to say that if you differentiate in Q direction, nothing would happen. Okay? So this is an operator that satisfies. It's not an algebraic operation, but well, I should write f prime times x for f in CQ. Okay? And so then the proposition says, okay, so let me call this condition here this one here. So in our application that we have in mind, okay, this one here always holds. Okay, and the class. So this is the class, the unit class, which is the class of the just the image of the identity class under this map. Okay, satisfies this one here. Sorry, this upper superscript 1 is just because it's actually an element of a one-parameter family of such operations. But I won't actually need the other one here. This is psi prime, and these are the derivatives, and this is a 1. So I just realized that okay. So okay. So this is the same linear second-order ODE that I wrote down before, except that d by dq has been replaced by this operation of differentiation. Okay? So this is something you have to prove. This is this one here. This is where the connection with enumerative geometry gets made. And it, of course, fundamentally, it's not surprising. It's a well-known fact that the symplectic cohomology of E, remember E is obtained from this E bar by removing a fiber, that the symplectic cohomology of E is closely related. Essentially everything you can do in it should be somehow expressible in terms of enumerative geometry of E bar, and this is, if you like, an instance of this. Okay? So this is how you get to this equation, and so what happens is
what was nabla 1 again?
Nabla 1 is this operation here.
But how was it defined?
Well, I didn't actually define it. Okay, so well, roughly speaking, so the clue lies if this lies in the kernel of this map. So what happens is you try to define such an operation in a naive way. Okay, this is supposed to. So there's an underlying chain complex, which has a base. It's a free chain complex of a C double bracket Q. In fact, it has a basis. Let's just take this basis and differentiate elements with respect to that. Okay, And then is this a chain map or not? So there's an obstruction for this being a chain map, which is in fact, the symplectic homology is naturally a Lie algebra. It's the Lie action of this element here. Okay? And so if this element is 0, you can sort of correct to make it a chain map. It's actually not, this is not completely canonical because, as you said, there's some correction term you have to add. But it's, I don't want to get it.
This is basically the quantum differential equation.
Well, no, because first of all, there's no equivariance here. Yeah. Okay? And also, it's always a second order equation, no matter which dimension you're in. So it's a little, it's really the fact that there's, after a change of variable, there's a trivial equation, second derivative is 0. And so, okay, so you get this equation here that governs, let's say like this, it governs the Q dependence of this element E. Okay? So the Q dependence turns out, so you can essentially write this element E as a Q expansion using solutions of this differential equation. And now you're here, and you could be in a slightly different situation. You could be here, you have this element here, and it turns out that that element is at least conjecturally related to the structure of the Fukaya category of the fiber. So from there on, the Q dependence of everything that you have really depends only on the Q dependence of E, and so this equation here turns out to govern everything that you have. And I'm already over time, which I apologize.